we're going to try and tie together kinetics with our next topic in equilibrium, with this idea of where does thermodynamics fit in all of this. And we looked at the first law of thermodynamics, which, all energy transfers have to add up to zero. But let's kind of see what else is at play. Since it's the first law, there must be a second. There is a third too. But anyway, so when we first studied chemical reactions, we just assumed that they went to completion. In reality, most reactions don't, like not all of the reactants that you have go into the products that the next chemical reaction shows. But instead, they reach a point of minimum free energy, and that is a mixture of reactants and products. And that point is called the equilibrium point. And at equilibrium, the reaction has not stopped, but rather the forward rate of reaction is equal to the reverse rate of reaction, and they're occurring at the same rate, so there's no net change in concentration macroscopically between reactants and products. So, sometimes after I say this, students are like, well, then why did we do a whole unit on chemical reactions and really this whole year on chemical reactions, assuming that all of those reactions went to completion? And well, for many reactions, it's pretty much, that's the true story. And if we look at it from the perspective of, if only one in a few trillion molecules doesn't react, it's not really worth talking about equilibrium. So a starting point for chemistry, the reactions that we looked at, is we call them spontaneous, and that they go to completion. And they're often referred to as like non-reversible reactions. And reactions which go to completion, they tend to produce one of three types of products. An insoluble precipitate, which is a type that we learned about, a gas that's allowed to escape. Most of the time we allow the gases to escape, and then combustion reactions, which is a huge part of what we've been studying this whole year. And all of those are non-reversible, and so therefore we didn't really need to talk about reversible reactions. So, this first one showing silver nitrate and sodium chloride, making sodium nitrate and the silver chloride pretty irreversible. When we've done this iconic reaction, magnesium and hydrochloric acid, releasing the hydrogen gas, not very reversible. And then when we light the Bunsen burners, we're not really gonna remake the methane. Most of that gets used up is heat and light, and we can't really reverse it. But other reactions do have some reactants and that remain in products. And so that's what we're going to kind of look at. But before we do, let's kind of talk about reaction spontaneity a little bit, since I threw that term out there. Okay, so spontaneous represents a change that occurs without outside intervention. So like rusting is spontaneous, okay? You leave something outside and it's made of iron, it'll oxidize in the air. And there's nothing you can do to stop it. It just happens on its own. So iron with oxygen is going to make that iron oxide. And it has a delta H value that's very negative. It's very exothermic, okay? Any physical or chemical change that once begun occurs with no outside intervention is considered spontaneous. And spontaneous changes only occur in the direction that lead to equilibrium. If you reverse the rusting reaction, the equation will not make the rust decompose spontaneously, okay, into iron and oxygen under ordinary conditions. You'd have to do some work there, okay? The formation of rust on iron is exothermic and spontaneous. The reverse reaction would be endothermic and non-spontaneous. So you could look at the reverse reaction, but it would be the opposite delta H. And since we know this reaction is spontaneous, the reverse would be non-spontaneous. So where did they come up with this though? Okay. Now, sometimes we say this and then you might say, oh, you might conclude that all exothermic processes are spontaneous and all endothermic ones are non-spontaneous. And that is not true either. So to remind you of this, okay, a physical process that is spontaneous is ice melting. Okay, that's an endothermic process from the particle perspective, and it is also spontaneous. The energy flows from the room into the ice, and it melts spontaneously. So what that says is that heat dispersion, hot to cold, can't be the only factor that contributes to the direction in which leads to spontaneity. So endo and exothermic processes can be spontaneous. Like when you mixed vinegar and baking soda, that was spontaneous, but it got cold to us, so it was an endothermic process. So that means something other than delta H has to play a role in whether or not a reaction is spontaneous, and that thing is called entropy. So entropy is considered a measure of the disorder or randomness of particles that make up your system. Okay, and particles that are more spread out are said to be more disordered and have more entropy than particles that are close together. The second law of thermodynamics says that spontaneous processes always proceed in such a way that the entropy of the universe increases. Positive. We're going to break that down, but that's what the second law says. So what that means is that putting something back together, making it more organized, gives an entropy value that's negative, and letting something be random is increasing the entropy, just so you understand the sign conventions there. So let's look at entropy a little bit more. So predicting changes in entropy, so how do you know if something is more entropic or less entropic? So the change in entropy, so change from products to reactants for your system or your chemical reaction. So if you're increasing the randomness, then the process is positive entropy and vice versa. So we can then predict a lot of them just by looking at chemical reactions, whether entropies can be positive or negative. So entropy does increase if a substance going from a solid to a liquid to gas, because there's more randomness in the particles. Liquids are more random compared to solids, and gases are more random compared to liquids. If you put a gas in a solvent, that always results in a decrease in entropy. And that's because the gas molecules are now in the liquid and they don't have as much freedom. So they're more organized, they have less disorder. Another idea of how you can predict entropy. So assuming there's no change in physical state, the entropy of a system usually increases when the number of gaseous particles is greater than the number of reactant ones. So this one has 2 moles worth of gas. This one has 3 on the product side. So we'd say the entropy is greater than 0. And the reverse would also be true. If you have less gas molecules on the product side, you would say the entropy has decreased. It's more organized. With some exceptions, we say the entropy increases when a solid or liquid is put into a solvent. So in general, you have a crystal lattice structure, the sodium chloride, and then if it dissociates, those ions have way more randomness than they did in the crystal structure. So entropy would be positive. And the random motion of particles of a substance, if you increase the temperature, they have more kinetic energy. And so the particles have more freedom. And so you would see the entropy increase. It's also worth noting that entropy is temperature dependent. And so you will see units for entropy that are in joules per Kelvin, because that's how much entropy a substance has and at that certain temperature. So this is where the third law of thermodynamics says that if you're at 0 Kelvin, so there's no particle movement, then it would have an entropy value of 0. But since you can't observe that, then it's just a theoretical value, the point in which there's no motion and everything is perfectly organized. So in a perfectly organized crystal lattice structure, the entropy would be given a value of 0. But as soon as you add kinetic energy to those particles, you're going to have some amount of more randomness disorder. And so entropy is 100% temperature related. And so you'll see units for that to qualify. So we need to know what temperature we're at to talk about the entropy. So breaking this down then again, the second law of thermodynamics says that the entropy of the universe must increase. And so when we're looking at the system and the surroundings, we have to see what's going on to determine if the overall process is spontaneous. Okay, so the change in entropy has to be greater than 0. However, the universe is the system and the surroundings. And so you have the change in entropy of the system and the change in entropy of the surroundings. In nature, the universe tends to be positive for all reaction processes. So entropy is increasing when you have something that's exothermic, because what that means is that the delta H of the system is negative, heat is released, which increases the temperature of the surroundings. And because thermal energy is the result of random motion of particles, the potential energy is dispersed and transferred as heat. So usually exothermic processes do increase the entropy of the universe. So the randomness or disorder of the system increases, and so also the delta H is positive. So notice that the delta H exothermic is a negative value, and delta S then is positive. So they have opposite sign conventions for what leads to spontaneity. So those two things are opposing factors. So if something's exothermic, you increase the randomness, then it's definitely going to be spontaneous. But how do you know if a reaction is spontaneous or not is based on the Gibbs free energy. And it basically puts the enthalpy change and the entropy change together in one equation. Free energy is energy available to do work, just in contrast. Energy related to entropy is useless because it's dispersed and can't be harnessed to do work. So the randomness, the heat is lost if you don't capture it. So how we put these together is we say you can predict the spontaneity of a reaction if you look at the change in Gibbs free energy. And so if this is a negative value and entropy is positive, so a negative minus it's going to be another negative to make it more negative. So that's where if delta G is negative, then a reaction will occur spontaneously. However, spontaneity does not tell us about how long it will take. A reaction could take a long time. Rusting can go over the course of, depends, what the surface, humidity, and whatnot. But it can happen over the course of hours, days, years, etc. But once it gets started, it will continue only in that one direction. That's what spontaneity says. So then we can look at kind of some conditions here. So if you have, you can look at this chart, but sometimes it depends on temperature and sometimes it doesn't. So it's because entropy depends on temperature. You kind of have to look at like which term is winning. So is it endo or exothermic? And so if it's exothermic, then, yes, it's going to be spontaneous, assuming entropy is also positive. So if you have negative delta H and positive delta, it's going to be spontaneous at all temperatures. And if you flip it, so if you have an endothermic reaction, so positive delta H and entropy is decreasing, stuff is becoming more organized, then it's going to be non-spontaneous at all temperatures. And then the other two scenarios where they're both positive or both negative, it's going to depend on the temperature. So which term is winning? Is the delta H winning or is the delta S winning? So we'll look at this and we'll put some numbers on it. So for example, okay, the delta H of a system is, so we already know it's endothermic, it's an endothermic process, but the entropy is increasing, it's a positive value. So is the reaction spontaneous overall? And we have the temperature in Kelvin. So delta G is the change in enthalpy minus the temperature times the change in entropy. So delta G here would be, we have to pay attention to these units here. Okay, so delta H is 145 kilojoules minus, we've got 382 Kelvin times the entropy is 322 joules per Kelvin. We're going to need them to be in kilojoules, so I'm also going to put that conversion in here, and so that it all lines up, so that the Kelvin cancels and the joules cancel. So we're subtracting kilojoules from kilojoules. Always pay attention to those units. So this term, the 382 here, is going to be 123 kilojoules. And so we can see here that which term is winning. Well, the 145 kilojoules is winning. The delta G here would be positive 21. Well, sorry, it's going to be 22 to the nearest whole number kilojoules. And this would be a non-spontaneous reaction. Delta G has to be negative. So the enthalpy here is winning over the enthalpy. And enthalpy is winning over the randomness factor. The heat going in to the system is greater than the randomness of the particles in the surroundings. So non-spontaneous at this temperature. If we increase the temperature, so we could figure out the temperature at which this term would then win, okay? But it's a higher temperature than 382 Kelvin. Another one, so you may have to find the delta H and the delta S. So this is putting together some of the ideas that we have done. So using our reference sheet from thermochem, so it's a good one that kind of bridges the kinetics and equilibrium here. But we're going to look at this reaction, sodium chloride forming into the elements that make it up, sodium and chlorine, and determine at room temperature what the delta G is. So we're going to have to look up the delta H of formation and entropy values. You could probably guess whether or not this is going to be spontaneous or not, since you're taking a crystal and breaking it down into the elements. It's probably not going to be spontaneous, but we can prove whether or not it is. So we need the delta H of formation of this, because it's going to be 0 for these. We can refer to our chart. Okay, so this is from the thermochem reference sheet, the pink sheet that you had. And so if we look up, sodium chloride here for the formation, remember that elements have 0. So I can see if sodium is even on here. Elements in their standard state are 0, but sodium chloride here is negative. The formation of it is negative 385. Let's see, is chlorine on here? And sodium, I don't think either one of those are on there, but they're 0 because they're in their standard state. And then we can also we'll look at the entropy values here in just a second, but you can refer to this chart. So this value is negative 385.9 units of kilojoules per mole. This would be 0 and 0 kilojoules per mole. So remember, delta H of formation is the sum of the delta H of formation of the products minus the sum of the reactants. So here, the delta H of formation, so it looks like a P, and the first one is supposed to be an F, would be the sum of the products, which is 0 kilojoules, and there's only 1 mole of this, so if I multiply by 1 mole, it's going to be minus the negative 385.9 kilojoules, which it's times 1 mole, so that's where the moles get canceled. So the delta H of formation for this, 0 minus the negative, is going to be positive 385. So this is a very endothermic process to take the sodium chloride and turn it back into the elements, and it would be exothermic. It was written in reverse. Now, overall, we want delta G. Delta G is delta H minus temperature times delta S, the entropy. So we also have to find the entropy here, and we get those values from a chart as well. So the entropy values, I'll highlight them here, and you can notice it's at 25 degrees. So you'd have to be, if it wasn't at 25, you'd have to be told the values. This chart's only good, but we want sodium as a solid, sodium chloride as a solid, and then chlorine. Where's chlorine? Oh, chlorine, Cl2 as a gas. So values of their joules per mole per Kelvin, and I'm going to go back and write them on our thing. So the change in entropy standard is going to be the sum of the products minus the sum of the reactants. Same thing, just with the entropy values. So the sodium chloride here is 72.1 joules per mole per Kelvin. The sodium is 51.4 joules, and these are not 0 because they have some entropy at different temperatures. Okay, so that's why these have values, versus the formation of them is 0 joules per mole per Kelvin. Okay, so then we're going to plug these values in. Now we have to multiply by, so this would be by 1 mole. So this is still going to be the 72.1. The sodium is still going to be the 51.4 because it'd be times 1 mole. But this we only have half a mole, so we're going to use half of that value there. So the delta S, the entropy here, is going to be the sum of the products. So 51.4 joules per Kelvin plus the 223 times half a mole. So we have plus 111.5 joules per Kelvin. That's the sum of the products minus the reactant, which is 72.1 joules per Kelvin. And you're going to get an entropy, standard entropy here, change of 90.8 joules per Kelvin, which I'm going to change that to kilojoules here because that's the value that delta G is usually written in. There's 1,000 joules in a kilojoule. So entropy value looks small, but remember you multiply it by the temperature, so 0.908 kilojoules per Kelvin. So to get the overall, and Gibbs free energy, is this spontaneous or not? We're going to then plug in our values. So we have the delta G, it's going to be the delta H, which we got the 385.9 kilojoules. So right now that would mean non-spontaneous, but minus this entropy term, 298 Kelvin times 0.0908 kilojoules per Kelvin here. And this term right here is only, it's a 27.1 kilojoules. So it's not big enough to weigh out this one. And so the overall delta G is positive 358.8 kilojoules. That makes this very non-spontaneous. So just so you can see the kind of problems that you have to do. Sometimes you're given the enthalpy and entropy value. Sometimes you have to refer to your chart. And it might have you solve for temperature. Okay, like it might give you the delta G, or it might want to be like, if delta G is at 0, then that just means it's at equilibrium, that it's the forward and the reverse are equal, and it would have to be negative in order for it to be spontaneous. There has to be a negative value. We have that. And then what we're gonna, so just to wrap this up, so a difference again about spontaneity and reaction rates is that, so spontaneous represents a change that occurs without outside intervention, but it occurs again only in the direction that leads to the equilibrium, the direction in which the reaction will proceed. But it doesn't say anything about the rate of the change, okay? So I like to use this example: logs in the forest slowly combine with oxygen in the air, and they will decompose, and that's spontaneous. But with the right conditions, they will combine with oxygen in the air and burn rapidly in the forest if they're ignited. But without that spark, the forest does not light up and burn. And thank goodness, because we need those trees to produce the oxygen to help us breathe. So saying that a change is spontaneous means only that the change will occur in a specific direction, and it will occur naturally and unaided once the reaction gets started. You have the right conditions for it. So a hot metal being placed in a beaker of cold water, and energy is transferred spontaneously from hot to cold. That's a change in enthalpy, and it happens spontaneously, okay? Chemical reactions proceed until equilibrium is reached, regardless of whether the reaction as written favors the reactants or the products. So if it's spontaneous, it means it's going to happen, and it's going to happen until equilibrium is reached, which is our next topic we're really going to dive into. But this helps you with linking spontaneity and reaction rates, and then where we're headed with equilibrium.